General properties of aqueous solutions. A solution is a homogeneous mixture of two or more substances. The substance present in the largest amount of moles is referred to as the solvent. The other substances present are called solutes. A substance that dissolves in a particular solvent is said to be soluble in that solvent. We are all familiar with these terms. If you think about it, when you mix some sugar into some hot water, the sugar is your solute, your water is your solvent. And we know that sugar is soluble in water, ergo it dissolves. Unless otherwise noted for this chapter, solution will refer specifically to an aqueous solution, i.e. where water is the solvent. Electrolytes and non-electrolytes. An electrolyte is a substance that dissolves in water to yield a solution that conducts electricity. An electrolyte undergoes dissociation and breaks apart into its constituent ions. For example, sodium chloride, when dissolved in water, will form sodium ions and chloride ions. Note that it is these ions that allow for the conduction of electricity. When a molecular compound with no charge forms ions, when it dissolves, this is referred to as ionization. On the other hand, a non-electrolyte is a substance that dissolves in water to yield a solution that does not conduct electricity. For example, sucrose, i.e. your sugar. When you dissolve it in water, it does not break apart into its ions. Rather, it remains intact upon dissolving. An electrolyte that dissociates completely is known as a strong electrolyte. These include water-soluble ionic compounds such as sodium chloride, which breaks down completely into sodium ions and chloride ions, strong acids such as hydrochloric acid, which breaks down into protons and chloride anions, and strong bases such as sodium hydroxide, which breaks down into sodium ions and hydroxide anions. What this means is that when you have a solution of any of these compounds, do not expect to encounter any full molecules in solution. They will all be ions. All strong acids are strong electrolytes. As there are not that many, I highly recommend you memorize all 7 of them. Note that sulfuric acid has 2 ionizable hydrogen atoms, and only the first ionization occurs completely, i.e. it is a strong electrolyte. However, the conjugate base is only a weak electrolyte, therefore the second proton is only slightly available in solution. A weak electrolyte is a compound that produces ions upon dissolving, but exists in solution predominantly as molecules that are not ionized, i.e. only small amounts of the molecule actually form ions. These include weak acids such as formic acid, which only forms small amounts of hydronium ions, or weak bases such as ammonia mixed with water to give you ammonium hydroxide. You may be wondering, how do we show that these are not predominantly ionized compounds? Well, in this chemical equation, you will notice that you have the double-ended arrow. This is called an equilibrium arrow. The double arrow denotes a reaction that occurs in both directions, as in the things on the left of the arrow are forming the things on the right, but the things on the right are forming the things on the left at the same time. When both the forward and reverse reactions occur at the same rate, the reaction is in a state of dynamic chemical equilibrium. Here is a nice flow chart to figure out whether you have strong electrolytes or weak electrolytes. You ask yourself, is the compound ionic or molecular? If it's ionic, it is a strong electrolyte. If it is molecular, you ask yourself, is it an acid, a base, or neither? If it's a base, it is a weak electrolyte. If it is neither, it is a non-electrolyte. Whilst if it's an acid, you ask yourself, is it one of the 7 strong acids listed in table 9.1? If you answered yes, it is a strong electrolyte. And if you said no, the compound is a weak electrolyte. Simple. Now moving on. Precipitation reactions. An insoluble product that separates from a solution is called a precipitate. This usually occurs when you are mixing 2 solutions which when mixed form a insoluble solid product. For example, in this picture shown, we are adding a solution of sodium iodide to a solution of lead nitrate, which when they mix forms a lead iodide precipitate, which is bright yellow. A chemical reaction in which a precipitate forms is called a precipitation reaction. Solubility guidelines for ionic compounds in water. Water is a good solvent for ionic compounds because it is a polar molecule. The polarity of water results from electron distributions within the molecule. The oxygen atom has an attraction for the hydrogen atom's electrons and is therefore partially negative compared to hydrogen, depicted here. Hydration occurs when water molecules remove the individual ions from an ionic solid surrounding them so that the substance dissolves. So we are saying that the solid that is being dissolved is the yellow and gray compound. The water molecules, shown in red and white, surround these ions individually. You'll notice that the yellow negatively charged species is surrounded by the partial positive charges of the hydrogens, whilst the positive gray ions are surrounded by the partial negative charge of the oxygens, shown in red. Solubility is defined as the maximum amount of a solute that will dissolve in a given quantity of solvent at a specific temperature. Here are two tables that are very good guidelines to show what compounds are soluble and what are not. Let's take a closer look. If you are wondering if your compound is soluble or not, look for specific ions. Water-soluble compounds will include alkali metal cations such as lithium, sodium, potassium, rubidium, or cesium, or the ammonium ion as the cation. Or they may contain the nitrate ion, the acetate ion, or the chlorate ion. It may contain the chloride ion, the bromide ion, or the iodide ion, with the exceptions of silver ions, mercury ions, and lead ions. As we saw before, lead iodide is a yellow precipitate. Also, most compounds containing the sulfate ion are soluble, with the exceptions of silver, mercury, lead, calcium, strontium, and barium, all of which are insoluble sulfates. On the other hand, if you want to know if your compound is insoluble, it's guaranteed to be insoluble if it contains the carbonate ion, the phosphate ion, the chromate ion, or the sulfide ion, with the exceptions of the compounds that have lithium, sodium, potassium, rubidium, cesium, or ammonium as the counterion, and compounds containing the hydroxide ion, with the exceptions of compounds with lithium, sodium, potassium, rubidium, cesium, and barium. I highly recommend you memorize these tables so that when you look at an ionic compound, you can state whether it is soluble or insoluble in water. Molecular equations. In a molecular equation, compounds are represented by chemical formulas as though they exist in solution as molecules or formula units. So for example, in this reaction, sodium sulfate plus barium hydroxide makes sodium hydroxide and barium sulfate. However, as we know, as we're denoted by the aqueous symbols and the solid symbols, the sodium sulfate is implied as being aqueous, but we know it's a strong electrolyte and therefore would form sodium ions and sulfate ions. But in this case, we are still representing it as sodium sulfate, the compound. Reactions in which cations in two ionic compounds exchange anions are called metathesis or double replacement reactions. Ionic equations. In an ionic equation, compounds that exist completely or predominantly as ions in solution are represented as those ions. So for example, in the reaction between sodium sulfate and barium hydroxide, the aqueous species are represented as follows. Sodium sulfate is split into sodiums and sulfates. The barium hydroxide is into barium and hydroxide ions, and sodium hydroxide into sodium and hydroxide ions. Of course, the barium sulfate, which remains a solid at the end, i.e. it's a precipitate, is not ionized and therefore remains as a full compound. Note that the complete ionic equation at the bottom looks a hot mess, but it is a much more accurate depiction of what is going on. Net ionic equations. An equation that includes only the species that are actually involved in the reaction is called a net ionic equation. Ions that appear on both sides of the equation are called spectator ions. So for example, we take the complete ionic equation, which looks like a hot mess, and we cross out the ions that we found on the left-hand side of the arrow and the right-hand side of the arrow. So for example, we find sodium ions on the left and the right-hand side, so we can cross them out because sodium ions are spectator ions. They are remaining in solution and they are doing nothing. The only ions that therefore are involved are the barium and the sulfate. And this is the reaction that is occurring. Barium ions are reacting with sulfate ions to form a barium sulfate precipitate. Precipitation reactions can be shown as molecular, ionic, and net ionic equations. To determine these equations, you must first write and balance the molecular equation, predicting the products by assuming that the cations trade anions. You then write the ionic equation by separating strong electrolytes into their constituent ions. Write the net ionic equation by identifying and cancelling spectator ions on both sides of the equation. If both the reactants and products are all strong electrolytes, all the ions in solution are spectator ions. In this case, there is no net ionic equation and therefore no reaction takes place. Moving on. Acid-base reactions. Acids can be either strong or weak. A strong acid is a strong electrolyte, as we've seen before. As you'll notice in this table, the strong acids is the list of 7 acids from previous slides that I told you to memorize. The strong bases are listed here on the right of the table, and they seem to be all the alkali and alkali earth metal hydroxides. Except beryllium, but we can ignore beryllium. Memorize these bases too. Strong bases are strong electrolytes, i.e. they dissociate completely. A weak acid is a weak electrolyte. It does not dissociate completely. Most acids, apart from the 7 strong acids that you are encouraged to memorize, are weak acids. They do not dissociate completely when in water. There are several different definitions of acids and bases. An Arrhenius acid is one that ionizes in water to produce hydrogen cations or protons. For example, hydrochloric acid gas will mix in water to form protons and chloride anions. This is an Arrhenius acid. An Arrhenius base is one that dissociates in water to produce hydroxide ions, such as sodium hydroxide. When it dissociates, it forms sodium ions and hydroxide ions. The Arrhenius definition is limited to protons and hydroxides in water. The Brønsted definition is a bit more useful. A Brønsted acid is a proton donor, whilst a Brønsted base is a proton acceptor. In these definitions, a proton refers to a hydrogen atom that has lost its electrons, also known as a hydrogen ion. For example, in this equation here, ammonia is reacting with water to form ammonium ions and hydroxide anions. The water is the Brønsted acid. It is donating a proton to the ammonia to form a hydroxide anion, whilst the ammonia is accepting a proton from the water, therefore it is a Brønsted base, and it becomes ammonium cation. Brønsted acids donate protons to water to form a hydronium ion, an H3O+. The hydrogen ion, or H+, proton, and hydronium ion, H3O+, all refer to the same aqueous species. The hydronium ion is the most accurate depiction of this. The hydrogen ion is what is being donated, and proton is just the most convenient descriptor of what a hydrogen ion is. The hydronium ion is the most useful as it takes into account the water and therefore makes it easier to balance the equation. In the equation below, we have hydrofluoric acid acting as the Brønsted acid. It is donating its proton to water, which is acting as the Brønsted base, to form a hydronium ion and a fluoride anion. A monoprotic acid is an acid that only has one proton available to donate. Hydrochloric acid is an example. It only has one hydrogen in the molecular structure that becomes one single proton in solution. A polyprotic acid has more than one acidic hydrogen atom. Sulfuric acid, H2SO4, is an example of a diprotic acid. There are two acidic hydrogen atoms. Polyprotic acids lose protons in a stepwise fashion. First, the sulfuric acid, H2SO4, will lose one single proton to form the hydrogen sulfate anion. This species will then deprotonate in a second step to form a proton and the sulfate anion. This second ionization only occurs to a small extent, and therefore we would say that hydrogen sulfate anion is a weak electrolyte. Bases that produce only 1 mole of hydroxide per mole of compound are called monobasic. Sodium hydroxide, for example, is a monobase. It only forms one hydroxide for every sodium hydroxide available. Some strong bases produce more than one hydroxide per mole of compound. Barium hydroxide, for example, is a dibasic base. Why? Its formula is BaOH2, in parentheses implying two hydroxides. Therefore, when it completely dissociates, it forms two hydroxides per mole. Acid-base neutralization. A neutralization reaction is a reaction between an acid and a base. Generally, a neutralization reaction produces water and a salt. So for example, if we have hydrochloric acid and when we mix it with sodium hydroxide, we will form water and sodium chloride. If we write the net ionic equation by removing the spectator ions, we will get the generic acid-base reaction, which is a proton reacting with a hydroxide ion to form water. Oxidation-Reduction Reactions. An oxidation-reduction or redox reaction is a chemical reaction in which electrons are transferred from one reactant to another. Oxidation is the loss of electrons, and reduction is the gain of electrons. This is often remembered as oil rig. Oxidation is loss, reduction is gain. What do we mean by this? Well, let's take this reaction here. We have zinc metal reacting with copper ions to form zinc ions and copper metal. The zinc starts the reaction being neutral and ends up having a positive 2 charge, meaning that it lost 2 electrons. This means that the zinc is oxidized in this reaction. The copper, on the other hand, starts with 2 plus charge and ends up being neutral. This means that it must have gained 2 electrons. Therefore, it is reduced. As the zinc is causing copper to be reduced, we would say that zinc is a reducing agent, whilst copper is oxidizing the zinc. Therefore, we would say copper is an oxidizing agent. Depending on the reactivity and electrode potentials of the metals, these reactions can occur spontaneously. For example, if we put a piece of zinc metal into a solution of copper sulfate, we will eventually replace the zinc with copper. A redox reaction is the sum of an oxidation half-reaction and a reduction half-reaction. So as we said before, the zinc is being oxidized to become zinc 2+. The half reaction would look like this. Zinc on the left-hand side with zinc 2+ cation and 2 electrons on the right-hand side. Whilst the reduction half reaction, we start with copper 2+ cations and we are adding 2 electrons to it to form copper neutral. When we sum them up, all we do is remove the electrons from the equation, kind of like spectator ions, and we end up with the overall redox reaction. Oxidation numbers. The oxidation number is the charge an atom would have if electrons were transferred completely. These help us keep track of charge distribution in our compounds. The oxidation number is sometimes called the oxidation state. To assign oxidation numbers, the oxidation number of an element in its elemental form is always 0. The oxidation numbers in any chemical species must sum to the overall charge of the species. Therefore, must sum 0 for any molecule, must sum to the charge of any polyatomic ion, and the oxidation number of a monoatomic ion is equal to the charge on the ion. Therefore, to assign oxidation numbers, you're better off knowing the elements that nearly always have the same oxidation number, which are here in this table. Fluorine is always -1. Group 1 and Group 2 metals are always 1 or 2 respectively. Hydrogen is practically always +1 unless when combined with Group 1 and Group 2 metals. At this point, hydrogen becomes -1. Oxygen is always -2 unless it is combined with something higher up on this list that requires it to have a different oxidation state. And finally, the other group 7 atoms, chlorine, bromine, and iodine, will always be -1 unless combined with something above on this list that require it to be a different oxidation number. For example, if we had to assign the oxidation number of the elements in the compound KMnO4, well, step 1 is that we start with the oxidation numbers that you know. K, potassium, is group 1, so it is always +1. Oxygen is usually -2. We notice that there are 4 oxygens, so we got to multiply the -2 by 4 to get a total contribution of -8. There's only 1 potassium, so that is +1. As -8 plus 1 equals -7, the charge of manganese, Mn, must be +7 because the overall charge of the compound is neutral. As there is only 1 manganese, its oxidation number must be +7. Let's do another one. Assign the oxidation numbers to the elements in the compound H2SO4, sulfuric acid. Well, step 1, we start with the oxidation numbers we know. Hydrogen is +1, oxygen is -2. Once again, there are 4 oxygens, therefore the total contribution is -8. There are 2 hydrogens, that is +2, to give us a total of -6. As the compound is neutral, the single sulfur must have a total contribution of +6, making its oxidation number also +6. Alright, how about we assign the oxidation numbers to the elements in ion ClO3-. Well, start with the oxidation numbers you know. Oxygen is always -2. Chloride, another group 7 species, should be -1. But because we have 3 oxygens, each with a negative charge of -2, making a complete charge of -6, but the overall charge of the species is only -1, it means that the chloride has to be +5, so that 5 minus 6, -1, is the total charge. This makes the oxidation number of chlorine +5. Here is a periodic table showing the oxidation numbers for each element. The most common ones are in red. You do not need to memorize all of these, as usually you are able to figure it out from context. Oxidation of metals in an aqueous solutions. In a displacement reaction, an atom or an ion in a compound is replaced by an atom of another element. So for example, when zinc reacts with copper chloride in solution, you form zinc chloride in solution plus copper metal. The zinc displaces or replaces copper in the dissolved salt. In this case, zinc is oxidized as zinc 2+, and copper 2+ is reduced to copper. When a metal is oxidized by an aqueous solution, it becomes an aqueous ion. So how do we know when a metal is going to replace another metal? The activity series is a list of metals and hydrogen arranged from top to bottom in order of decreasing ease of oxidation. Metals listed at the top are called active metals, whilst metals listed at the bottom are called noble metals. An element in the series will be oxidized by the ions of any element that appear below it in the table. So as we see, zinc is at the top of the list, whilst copper is third from bottom. Therefore, if we add copper ions with zinc metal, the zinc metal will replace the copper ions to form zinc ions and copper metal. If we reverse this and add copper metal to zinc ions, there will be no reaction because copper is lower down the list than zinc. Here is another activity series. Which of the following reactions will occur? Cobalt mixed with barium ions, tin mixed with copper ions, and silver mixed with sodium ions. Well, as we can see, barium is higher up than cobalt, so therefore no reaction will occur. Tin will replace copper because tin is higher up than copper in the series, and silver is below sodium in the series, therefore no reaction will occur. Here is a more complete activity series list. If you ever get a question about displacement reactions, expect to get an activity series given to you, whether it is the complete one or a partial one. Balancing simple redox equations. Redox reactions must have both mass balance and charge balance. Therefore, in this case, for example, chromium reacting with nickel ions to form chromium ions and nickel solid, the oxidation half of the reaction forms 3 electrons, whilst the reduction half forms 2 electrons. Before adding half reactions, the electrons must balance. Therefore, prior to adding the 2 half reactions, we must balance the electrons. We must multiply the oxidation half reaction by 2 and the reduction half reaction by 3 to yield us 6 electrons in each. We can now cancel them out, but we'll notice that the equation itself now has 3 nickel 2 plus ions plus 2 chromiums gives us 3 nickels and 2 chromium 3 pluses. This is known as the half reaction method. There are several other types of redox reaction. For example, combination reactions, where 2 elements combine to form one molecule. In this case, nitrogen reacting with hydrogen to form ammonia. Hydrogen is being oxidized from 0 to +1, and nitrogen is reduced from 0 to -3. Decomposition can also be a redox reaction. For example, in this case, sodium hydride is forming 2 sodium metals and 3 hydrogen gases. The sodium ion in sodium hydride is being reduced to sodium, and the hydride anions are oxidized to become hydrogen gas. Disproportionation reactions occur when one element undergoes both oxidation and reduction. So for example, this hydrogen peroxide here breaks down into water and oxygen gas. The oxygen in hydrogen peroxide has an oxidation number of -1, whilst in water it becomes -2, and in elemental oxygen it becomes 0. So from hydrogen peroxide to water, the oxygen is being reduced, whilst from hydrogen peroxide to oxygen it is being oxidized. Combustion, or the burning of a compound, is also a redox process. For example, in this case, methane gas reacting with oxygen gas to form carbon dioxide and water, we see that the carbon is being reduced from a -4 oxidation state to a +4 oxidation state, whilst the oxygen is being reduced. Moving on. Concentrations of solutions. Molarity, big M, or molar concentration, is defined as the number of moles of solute per liter of solution. So mathematically speaking, molarity equals moles of solute divided by liters of solution. Other common rearrangements of this equals liters of solution equals moles of solute divided by molarity, or moles of solute equal molarity times liters of solution. Dilution is the process of preparing a less concentrated solution from a more concentrated one. However, the number of moles of solute before dilution is equal to the number of moles of solute after dilution, i.e., we are not changing the number of moles, we are just changing the amount of solvent and therefore decreasing molarity. So for example, in an experiment, a student needs 1 liter of a 0.4 molar potassium permanganate solution. A stock solution of 1 molar potassium permanganate solution is available. How much of the stock solution is needed? Well, we must use the relationship that moles of solute before dilution equals moles of solute after dilution. Since the number of moles of solute equaled the molarity times the liters of solvent, if moles of the concentrate and the dilute are equal, we can set the molarity of the concentrated sample times by the liters of the concentrated sample equal to the molarity of the dilute sample times the liters of the dilute sample. As we know that the concentration of the stock solution is 1 molar, and we want a dilute molarity of 0.4 molar and 1 liter of it, we can put these numbers into the equation and solve for the number of liters of concentrated needed. Turns out that when we put the numbers in, the amount is 0.4 liters, so 400 milliliters. Therefore, what this is telling us is we need 400 milliliters of the stock solution in a 1 liter volumetric flask, and then we top it up to the 1 liter mark to have a solution of 0.4 molar potassium permanganate. Because most volumes measured in the lab are in milliliters rather than liters, it is worth pointing out that the equation can be written as molarity of the concentrated sample times by the milliliters of the concentrated sample equals the molarity of the dilute sample times by the milliliters of the dilute sample. You are not limited to one dilution. A series of dilutions that may be used to prepare a number of increasingly dilute solutions is called a serial dilution. Step 1 is to prepare a dilute solution from the stock solution. Step 2 is to dilute a portion of the prepared solution to make a more dilute solution. And step 3 would be repeat as needed, so you dilute it as many times as you need. This serial dilution is also the principal concept in homeopathy. The pH scale. The acidity of an aqueous solution depends on the concentration of hydronium ions, H3O+. The pH of a solution is defined as the negative base logarithm of the hydronium ion concentration in moles per liter, i.e. pH is negative log of the concentration of hydronium ions, and the concentration of hydronium ions is 10 to the negative pH. In pure water at 25 degrees Celsius, the concentration of hydronium ions is log 1 times 10 to the negative 7. Therefore, the pH equals negative log of 1 times 10 to the negative 7, which equals 7. pH is a dimensionless quantity, i.e. it does not have units. Here is a table showing your pH scale and which concentrations are acidic and which concentrations are basic, along with the corresponding hydronium ion concentrations. Notice that the powers of the hydronium ion concentrations are the negative values of the actual corresponding pH values. So for example, pH 13 has a hydronium ion concentration of 1 times 10 to the negative 13 molar. To put the pH scale into perspective, here we have some common fluids and their pHs. Something very acidic, such as stomach acid, has a pH of 1. Lemon juice has a pH of 2. Vinegar has a pH of 3. Rainwater in clean air actually has a slightly acidic pH of 5.5. Milk has a pH of 6.5. Pure water is neutral at 7. Tears are slightly acidic at 7.4. And ammonia used to clean around the house has a pH of 11.5. Aqueous reactions and chemical analysis. Gravimetric analysis is an analytical technique based on the measurement of mass. Gravimetric analysis is highly accurate. However, it is only applicable to reactions that go to completion or have nearly 100% yield. The most common types of reactions that can be studied by gravimetric analysis are ones that form a precipitate. You would run the reaction and then isolate your precipitate, filter it out, for example, dry it and weigh it, and then use that mass for any calculations you may have to do. Acid-base titrations. Quantitative studies of acid-base neutralization reactions are most conveniently carried out using a technique known as titration. A titration is a volumetric technique that uses burettes. The point in the titration where the acid has been neutralized is called the equivalence point. The equivalence point is usually signaled by a color change. The color change is brought about by the use of an indicator. Indicators have distinctly different colors in acidic and basic media. The indicator is chosen so that the color change or end point is very close to the equivalence point. Phenolphthalein is a common indicator. Sodium hydroxide solutions are commonly used in titrations. Sodium hydroxide solutions must be standardized as the concentrations change over time. The sodium hydroxide reacts with carbon dioxide in the air that slowly dissolves into the solution, forming carbonic acid. The acid potassium hydrogen phthalate, KHP, is frequently used to standardize NaOH solutions. Here is a depiction of KHP, and the acidic proton is indicated, making it a monoprotic acid.